We can now describe the main step that introduces error, meaning quantization, and it's also the step that actually allows us to compress a lot. Without quantization, we won't be able to compress too much. We will be able to compress, but not as much as we see in our digital cameras. So basically, we have the forward transform, which we have seen. We have this, we have seen earlier, but now we're going to describe the quantization. So let's talk about it. And we have actually already seen quantization when we started talking the very early weeks of this class, but let's just describe it in detail in the context of JPEG compression. So remember, we started from an 8x8 image, and we have that and transform. And what I'm going to represent here are the transform coefficients. So just in the previous video, we saw that we actually have the transform coefficients, and we get them as a double sum. We sum over the x, we sum over the y, we sum over the coordinates of the image, and we're basically summing the image. This is the image, and we had basically the cosine basis. So that's how we got to these coefficients that we represent here. We start from an 8x8 and we get 8x8 coefficients. So we have kind of an image in a different domain, in the cosine domain. So what we have here are different things that we could do to those coefficients. Now we are working with the coefficients. So for example, we could say that we are only going to take the coefficients here, and we'll ignore all these other coefficients. That would be very, very simple. Say, go to the upper left corner and only use those coefficients, ignore everybody else. And I'm going to write in a second what that means. We could also do this, which is somehow I'm going to say which coefficients to take. Those that are shaded or says 1 are going to be coefficients I'm going to send. Those that say 0 or unshaded coefficients I'm not going to send or store. Now we can do something else, and we can say, you know what? I don't want to include or discard coefficients. I want you to take this coefficient up here and represent it with 8 bits. So I'm going to let you to do quantization to 256 levels. On the other hand, this coefficient that shows up here, so that will be the coefficient 07, T07, I want you to use only 1 bit. So you're going to only be able to represent 2 different levels for that coefficient. And we're going to talk about this in a second. Now, what happens when we do quantization? Remember that f is going to be then reconstructed, as we saw in the previous video, as the sum of t, the transform coefficients. And we can put r because you remember that the forward and inverse were basically the same. So this is how we are going to reconstruct our image. Now, if we quantize t, we're not going to reconstruct f because we're going to have an approximation of t, and then we're going to reconstruct an approximation of f. And remember, what's happening is this. Our f is a linear combination of the coefficients, either the original coefficients or the quantized coefficients, a linear combination multiplying the bases. And these are the bases. So here I'm just drawing them in a 4x4, but we know that we are talking 8x8. So this top coefficient basically says how much of these bases we are going to be using. And you can say, you know what? Maybe our visual perception is such that if instead of what I wanted to use, which is 7.7 times this basis, maybe if I do 7.5, it's not such a big deal and my visual system won't perceive the difference. So that's the idea of quantization, to basically round or say, if I put a slightly different number of this component, whatever component TUV represents, it might not be such a big deal in the reconstruction. And we're going to see that. Now, remember, why are we doing quantization? We're doing quantization because we're going to do Huffman coding after that. And remember, in Huffman coding, we want a non-uniform distribution. We want some coefficients to appear a lot, so we're going to give a short code, and some coefficients to appear not much, so we can give them a long code. For example, if we quantize a lot, we might find out that 7, 8, 9, 10 all become 0. And then we're going to be able to basically compress a lot. And we're going to see a bit more examples of that in the next transparencies. Now, this is the basic idea. As I say, we are going to quantize, we're going to change the coefficients that hopefully we are not going to notice that. Now, there is something I want to call your attention, something which is very smartly done in JPEG. If we just do quantization, we still have to send an 8x8 matrix of quantized transform values. Means I have to send 64 numbers. Now, I started, let's say, from an image that has 8 bits per pixel, 256 gray levels. Then I need to send each one of these, even if I'm going to use only 1 bit, as it says here. So I started from 8 bits, and I can use 1. Then I can only compress 8 to 1. I have to basically send you that value. JPEG says something very smart. As we're going to see in a second, the top region is going to use, as is represented here, more bits. The quantization is going to be more fine. In the lower corner here, JPEG is going to say, you know what, I'm willing to do very, very drastic quantization. So drastic that a lot of the TUV, the coefficients, will become 0. So JPEG is not going to encode, it's not going to store this, then this, then this TUV. It's going to actually go in a zigzag fashion. It's going to say, okay, first, I'm going to just do a convention. The first coefficient you see is this, which is T00. The second coefficient you see is this one, which is T01. The third coefficient you see is this one, which is T10. Okay, so you're going to be basically be encoding the quantized 00. Then you're going to be encoding the quantized 01. Then you're going to be encoding the quantized 10. And then you keep going in this zigzag fashion. Now, why is that important? As I say, a lot of these are going to become 0. Their value is going to be 0 after we do a very strong quantization there. So when JPEG arrives to a certain coefficient and sees that everybody else that come after becomes 0, it just puts one signal that says end. And if the end is here, meaning everybody here is 0, then I save a lot of bits. Instead of sending 1 bit for each, let's say, to say 0, 0, 0, we basically send one end. And that means to the end of my block, to the end of my 8x8 transform coefficients, everybody became 0. And that's a very smart thing, and that's what allows us to go beyond 8 to 1 and to very, very high compression ratios. And the more you quantize in this region, the earlier this end symbol will appear. So that's the basic idea of quantization, but let's just see how we do it. So a very simple form of quantization is what we have here, and that's called uniform quantization. And this is basically what JPEG is doing. It's saying, okay, you take your coefficients. I want to do uniform quantization in the sense that, let's just pick, for example, this interval. It's saying everything that falls in here, every coefficient that has values between this point and this point, I'm going to represent with this. So that's basically very important. So now I'm going to help Huffman coding. No matter what you are, you're going to be represented by one number. So I'm basically going to increase the probability of that number appear. Instead of having a lot of numbers appear very few times, I have one number appears a lot of times. And that's very important, as we know, for Huffman coding or for any coder that will show up at the last stage of compression. Now, everything, for example, in this interval from here to here will be represented by this value. And the way JPEG does that, and many other coders, is saying, okay, I'm going to give you numbers that you're going to scale by that number. Okay? And let's just, so basically, it says that the T00, the T00 is going to be divided by 16. We saw that early on in one of the first videos. It's going to be rounded, and then it's going to be multiplied by 16 again, and that basically became my new T00. Very simple operation, but very efficient. Maybe not ideal, maybe not the best I could do, but JPEG is motivated as not only by doing good quality, but also by simplicity. And we have seen what this makes coefficients do. So as we see here, if T00, basically every number between 0 and 15 will become 0 with this operation. So if I have 7 divided by 16, it's a number that when I round down, it becomes 0. I multiply by 16, and it becomes 0, stays 0. So basically, every number here became 0. So every number then between 16 and 31 became 1. So I'm basically quantizing, and I'm helping Huffman to basically have less numbers to send and also more concentration. And the more we scale by, so for example, if we scale by 100, means every number between 0 and 99 will become 0. So my quantization is much more broad. It's not as fine, but hopefully if I do it correct, I won't notice too much. So that's a basic idea of JPEG quantization. So it's going to give, and I'm going to show the default table in JPEG in a second. It's going to do this. And remember what I said in the previous slide, because you're going to quantize a lot, the high ones, a lot of these are going to become 0. And then this end of block signal is going to be very powerful to compress a lot of symbols, with a lot of coefficients, a lot of TUV, a lot of transform coefficients, with just one symbol. Extremely powerful. So let's just give an example. This is done actually with the previous matrix. And the basic idea, and this is how JPEG basically operates, it's going to do the following. It's going to take this matrix, and I'm going to show the matrix for JPEG in a second, as I say, and say, okay, let's just do it. Let's just divide by 16, 11, 12, 12, and so on. Or I can tell you to divide by twice this matrix, so by 32, 22, 24, 24, and so on. So let's see the effects of that. So here, we basically progressively are dividing by the same matrix, but scale up. And we see how the quality degrades. Of course, we are not going to want to do this. What probably happened here is that we end up multiplying by 32 times z, so we end up basically destroying most of the coefficients. But if we basically don't multiply by too much that matrix, so we can scale down, divide by 16, divide by 11, multiply round, multiply back, and get very, very decent quality images. The more we divide, the more we compress. So if we, as we saw in the previous slide, if we are going to divide by 2, we're only rounding, basically. If we're going to divide by 100, we're basically making these blocks of numbers become all equal. Or if we want to see this in the graph, the larger this is, the more we are quantizing. And this is, as promised, the default table that JPEG is going to use, or one of the possibilities for the default table. And the reason I'm showing it to you is because, once again, I want to show you how numbers increase, they decrease back, and there has been a lot of studies on this, but still the quantization is uniform. And once again, you can basically do multiplications of that matrix. So this is what you're going to get with one scale of that matrix. And then if you scale it more, you're going to get, and I hope you can see the quality, and this is the error, just in case it's hard for you to see from the image. But let's just concentrate on certain regions. We see here, it looks very nice. So probably we haven't scaled the quantization matrix too much. Here, we actually scale it too much, and it doesn't look very good. Look at this zoom in region. It really doesn't look very good. Also here, if you zoom in, you can see some problems with the image, but not at this scale. So basically, what we have is a quantization matrix that says every one of the transform coefficients, T, U, V, what do we want to do? Do we want to divide it and round and divide it by 5 or divide it by 100? And the larger the number we divide by, the more error we are producing, but of course, the more compression we're doing. So it's interesting, in some of the software packages that you have out there, when you're saving an image, it asks you for the quality that you want to save your JPEG image with. And what's asking you is basically how much to multiply this quantization matrix. So the quantization matrix is basically, in that package, is a fixed matrix. So how are you going to basically compress more or less? By scaling up or down that quantization matrix. So when it says you want high quality, it's not going to scale by a lot. When it says you want high compression or lower quality, it's going to scale it by a lot. And that's how JPEG works, with a very simple, basically uniform quantization that is done just by scaling and multiplying back. Of course, the multiplication is done at the decoder. So every number between 0 and 100, if you scale by 100, between 0 and 99, sorry, if you scale by 100, is going to be coded at a 0, and then the decoder is going to multiply by 100 to get the number back. So that's what JPEG does for quantization, and that's where you get the compression. Now, I want to mention that there are techniques and there are theories to try to basically adapt the quantization to the signal type. So JPEG does a uniform quantization because it's very simple. We don't have to do a uniform quantization. We can have intervals, as shown here, that have basically different width. So some regions will be basically scale more than other regions. That doesn't happen in JPEG. It's uniform. No matter what value is T, U, V, you always divide, for a given coefficient position, you always divide by exactly the same number. Now, here, depending on what's your input, the value you're going to be dividing by. And that's very important that JPEG decided not to do that, once again, in part because of simplicity. But I want to conclude this chapter on quantization by explaining to you that you could actually do better if you were willing to spend a bit more complexity in your algorithm. And basically, there is very nice theory on how to do better, and that's called the Max-Lloyd Optimal Quantizer. And the basic idea is relatively simple, although computations are not always straightforward. And what they have shown is basically, remember, if you want to measure the error as the square difference between a given pixel and its representation, and we talk about the square. So that's the way you decide. You say, I want to do the best possible quantizer considering this error. And considering that I have certain allocations of bits. Of course, if you say, I don't care how many bits are used, then don't quantize at all. That will be basically zero error. But if you come and tell me, I can only use basically 256 levels. So I can only use 8 bits. So I can only have 256 of these intervals because I need to represent each interval by one of my strings of bits. And so you predefine the number of levels that you're willing to use, the number of intervals, and you predefine this as your error. So you can show that basically what we have to do, and this is very intuitive, is say, okay, what's the error I'm making in every interval? So you're going in every one of these intervals. So I'm going to do S sub I minus 1 over S sub I. That's my integration. And you can show that if this is the error that you care about, then here you have to put S minus, basically it's only S, because I'm going to do an integral, minus T sub I. So that's the error. You get S, you represent it with T. So that's your error, but you have to also multiply by the probability of that value appearing. If it never appears in your input data, then you don't care about it because you're never going to make an error. And then you integrate over S. So that's one equation, looks how the unknowns, which is the borders of our interval that we're trying to find, appear here in the integral part, and the representative appears here. So this is only one equation, but we can get a second equation. You can actually show that the SIs are the average of the TI and the TI plus 1. And that comes because you're trying to compute that mean square error, and that leads to average. And then from this, you're going to get a second equation. So you get basically two equations for every one of these concatenated intervals, and you have to solve them. And that's not always easy, and closed solutions do not exist for most of the probability distributions. But they do exist if we assume that the probability distribution is uniform. And that's what basically JPEG is using. It's saying, okay, the probability distribution is uniform, so I'm going to just do the rounding as I explained before. But there is good theory represented here basically in these equations that if you knew the probability distribution, you can actually do better than just uniform quantization. But once again, JPEG decided to do uniform quantization, and that's both for simplicity and also what's called universality. I don't need to know the probability distribution. I'm going to make JPEG work very good for basically almost any image. Maybe I could have done it better for some distributions, but I'm going to just make it basically work for any distribution. And I should say to you that you can modify JPEG, and that's still part of the standard, and introduce your own quantization tables, which might follow a distribution that you know. So if you're compressing a very particular class of images, you can basically tune your JPEG to do that. So with this, basically, we have concluded the basic underlying concepts of JPEG. We start from a transform, which is DCT. We quantize uniform quantization. We do Huffman coding. Very, very simple. And you're going to have as one of your optional programming exercise to actually build JPEG. And it's not going to take you long. If you use, for example, a software like MATLAB, you're going to do a DCT, which is a very simple command. You're going to do a quantization. Remember, it's nothing else than divide, round, and if you're already playing the decoder, multiply back by the same number. And then you can do a Huffman coding. But even without the Huffman coding, you will be able to see when you divide by larger numbers, you basically get more compression, but less quality. Thank you.